Hello, everyone. This is going to be our video for part 2 of the Unit 3 notes, talking about spectrophotometry and the Beer-Lambert law. So spectrophotometry is used specifically because many solutions have very distinctive colors, and they're going to absorb and transmit different wavelengths of visible light. The intensity of the color of the solution is indicative of that solution's concentration, which kind of makes sense, right? If a solution is more concentrated, it's going to be a darker solution. If it is less concentrated, it's going to be a lighter solution. So the way that spectrophotometry works is basically you have a light source that's going to emit some light. And that light source is going to hit a filter that's going to filter all of that light for a very specific wavelength of light, which is going to be allowed through that filter, and it's going to hit a sample, which has a solution in it. Now that solution is going to absorb some of that wavelength of light, and it's going to transmit some of that wavelength of light. And the sensor on the other end can give an absorbance or transmittance value, depending on what you ask the spectrophotometer to do. Okay, so it is, in essence, a quantitative or numerical method of studying matter. And again, like I said before, it's going to yield a numerical value that describes the amount of light that passed through or was absorbed by that solution. So here down at the bottom, we have a much better diagram than I could ever draw that describes what I just did. Your light source shining a bunch of light through a filter, which filters out one specific wavelength. In the case of this diagram, it's the red one that's going to hit our sample. That sample is going to absorb a little bit of it. It's going to transmit some of it and hit a detector, which will give us that reading. Okay, so just as a review, the electromagnetic spectrum ranges from radio waves to gamma rays, visible light being right there in the center. Now, how do spectrophotometers work? So if you were here on Monday and Tuesday for the lab, you probably recall my rant about how terrible our spectrophotometers are. But newer ones look something like you're seeing on the right here. They have a place to put a cuvette, which is this little square thing, and light can pass through the clear sides of that cuvette. So our general procedure is sample is placed into the cuvette. You select a wavelength at which to analyze your sample. Your instrument measures the amount of light absorbed by that sample. So that's basically how that works. We also use in a spectrophotometer a negative control or a blank cuvette. That blank cuvette represents everything except the sample that we're testing. So let's say I put some chemical in some other chemical, right? And chemical A, which is whatever's red over here, is the thing that I am trying to test. But the other chemical B that it's in, I don't want that chemical B to affect anything else of my reading. I only want it to take values that are attributed to chemical A. So if I put chemical B in this blank cuvette and tell the spectrophotometer to ignore anything associated with B, then it's only going to give me a reading that's associated with A, which is what I want. So that was a very complex explanation, but basically it's calibrating the machine properly. So in our case, our reference blank is water because the chemical that we're testing, the copper sulfate, is placed in water. So we made water our blank to calibrate that machine properly. Kind of like you can think of it similar to using a balance and a weigh boat. If you want to weigh a sample in a weigh boat, you have to zero out the weight of the weigh boat before you take that mass, that measurement, or you have to subtract it out later. Either way, you have to get rid of the weight of the weigh boat somehow, some way, before you can get an accurate measurement. Here is another diagram representation. I'm not going to go over that again, but what I would really like to point out is that there is a relationship between absorbance and transmittance. So absorbance is the same thing as the negative log of transmittance. And this one seems a little bit more complicated, but this is our relationship that we are going to utilize in the homework practice. So how do you choose a wavelength? you can choose a wavelength based on an absorbance curve, which you could look up for a particular element. You're going to look for peaks on that absorbance curve, your max absorbances. So a wavelength that's somewhere around on this graph, 460 or so, or a wavelength around 660 or so would be an appropriate wavelength to analyze whatever compound this happens to be. This is going to be your better one, but this one could also be workable as well. But if you don't have an absorbance curve, it is easy to look up the proper wavelength to analyze a sample at for any particular chemical. So either you're reading one of these graphs or you are looking up that information. For our copper sulfate, wavelength 635 nanometers is going to be our lambda max, or our max absorbance wavelength. Beer's law describes the relationship between absorbance and concentration of a solution. So we have A for absorbance is equal to the molar absorptivity constant, which is something that you either have to calculate or have to be told, times the path length. How far does that light have to travel? Usually it's 1 centimeter, unless you are told differently, and then times concentration in moles per liter. So this path length is in centimeters. Our solution concentration is in molarity, moles per liter. Our absorbance is usually unitless, meaning it does not have to have a unit attached to it. And our molar absorptivity constant has to have a fairly complex unit attached to it, because of course it does. And that unit for our molar absorptivity constant is generally going to be liters per mole times centimeters. Wow, that looks terrible, but liters per mole times centimeters, okay? If you do not remember that later, you are free to look it up and it will be given to you on an exam, okay? So moving on, what does that even mean to us though? Why do we care about using Beer's law to do those calculations? Well, whoops, went too far. There is a direct relationship between absorbance of a solution and concentration, which again, it kind of makes sense because again, concentrated solutions are darker and therefore would absorb more light than they would transmit. So it makes sense that we have this positive slope of the line that you're seeing on the right. Okay, so this graph is telling us at certain concentrations what are the absorbance values. And then off of that, this trend line has an equation of y equals 34.27x plus 0.0032. So you can actually use this equation to predict unknown values. So this is a very important bit of information that you'll use multiple times. This y equals mx plus b format here that you're seeing in the graph corresponds directly to values in Beer's law. Your y value is the same as absorbance. Your m value is going to be the product of your molar absorptivity constant and your path length. And your x value is going to be concentration. So here is x, concentration. And this 34.27 is the product of E times L, and our y is our absorbance value. So if I were to give you an absorbance value and ask for the concentration, you could absolutely calculate that. If I were to give you a concentration and ask you about absorbance, you could absolutely calculate that. And you can do it on the graph too a little bit. It's just not going to be very accurate. This equation would give you a more accurate value. So method one, again, graphing. You can prepare your plot, you can determine your equation of the line, measure an absorbance, and use your absorbance measurement to solve for the concentration of an unknown, which is exactly what we did in the lab on Tuesday. So to do that, your first step is to take your absorbance value, and you are going to look for approximately where that's going to fall on your graph. So if I have about 0.25, which is a little low on here, it'd be more like up here actually. Where is that going to fall on my concentration? So looking here, I know that my concentration that I get out of this equation should fall somewhere between 0.006 and 0.008. So my absorbance value is the same thing as y, so I can go 0.25 is equivalent to 34.27x plus 0.0032. And I can do that math and I can solve for x, which is the same thing as concentration. And when I do that, you should get x is equal to 0.0072, which makes sense because that falls directly in the range that we said that it would be in just by estimating using the graph. Okay, method 2, if you don't have access to one of those graphs, you can use proportionality if you have enough information to do so. Absorbance 1 over absorbance 2 is equivalent to concentration 1 divided by concentration 2. So if I were to give you 3 out of 4 of those values, you could set up a simple proportion to solve for the fourth one. So this problem says calculate the concentration of a solution of cobalt 2 chloride that has an absorbance value of 0.4 at our max absorbance if a 5.00 times 10 to the negative 3 moles per liter solution of cobalt 2 chloride has an absorption of 0.175 under the same conditions. So these two bits of information are linked. This is absorbance 1 and concentration 1. So absorbance 1, 0.175 is equal to concentration 1, 5.00 times 10 to the negative third. Absorbance 2 is also given to you 0.400, and we're solving for C2. So if you do cross multiplication, you can easily solve for that value, which should turn out to be that value down there, 0.0114 moles per liter. If you don't know how to solve a proportion, feel free to talk to me about it. I'm happy to walk you through it. Sample problem number 3 is just straight up using the Beer's law equation, which again is listed for you in the upper right. Absorbance equals molar absorptivity times path length times concentration. This seems like one of the simplest methods. However, this molar absorptivity value is usually not readily available, which is why we do spectrophotometry to create that line and use that trend in the first place. So if it is given to you, however, like it is in this problem, you can absolutely use Beer's law to solve. So this says the molar absorptivity of ethanol in hexane is at its lambda max. It's 15 liters per centimeter times moles. Calculate the concentration of ethanol, sorry, that should be an O, in a solution that has an absorbance of 0.652 with a path length of 1.2 centimeters. So we have absorbance, we have path length, we have that funky E, and I can calculate for concentration. 0.652 is equivalent to 15, that's that E, times 1.2, which is our path length, and we're solving for concentration. So once you do that all out, you should figure out that this is your concentration in moles per liter. Now, I know I went kind of fast, but these are plug and chug equations, so they should not be very difficult for you to plug in. The difficulty is going to come when you have to convert before using them, as it always is. So don't forget that conversions exist and you will have to do them. You might have to convert milliliters to liters before doing anything, or milligrams to grams, or maybe even grams to moles, potentially. So hopefully this is helpful. Again, if you have questions, please talk to me about it next week.